So far, we've only dealt with power series that have had constants in them, right? We had the index, the n, and that sort of changed for every term. But it wasn't like the entire series, the sum itself was changing, right? In this and the following lectures, we're going to be talking about functions which are defined by powers, or are defined by infinite series. So today we'll just concentrate on one type called power series. This isn't the only type of function that is defined by a series, but it's one type. Sort of the most common and important. So it goes like this. Let A be any real value whatsoever. A power series centered at A is a function defined via a power series. F of x equals the sum from n equals, let's say, 0 to infinity of Cn x minus a to the n for some sequence of real numbers Cn. Okay? And these Cn, these are constants. These don't depend on x. The only dependency on x is right here. These Cn's are called coefficients of the power series. All right? So let's just look at what one of these might look like. For example, you could have something that looks like f of x equals the sum from n equals 0 to infinity of x to the n divided by n factorial. This is an example of a power series, because in this case we have the sum from n equals 0 to infinity of 1 over n factorial times x minus 0 raised to the n. Okay, so in this case, we have a power series centered at 0, and the coefficients are just 1 over n factorial for all the non-negative n. By the way, 0 factorial is 1. That's something that I should mention right now, and it's going to come up later. So yes, 0 factorial is defined as 1. Okay, so in other words, this is the sum. So it's 1 over 0 factorial, which is 1, times x to the 0, so that would be 1, plus 1 over 1 factorial, that would be 1, times x to the 1, which is just x, plus 1 over 2 factorial, okay, that's 1 over 2, x squared, plus 1 over 3 factorial, that's 1 over 6x cubed, plus 1 over 4 factorial, that's 1 over 24, x to the 4th, plus 1 over 5 factorial, that's 1 over 120, x to the 5th, plus dot, dot, dot. Okay? This looks an awful lot like a polynomial, doesn't it? It is. Well, it's like a polynomial in the sense that it's a bunch of powers of x, integer powers of x, multiplied by some constants and then add it all up. But now it's infinitely many of them rather than finitely many of them. So in some sense, you could think of a polynomial as a special case of a power series. A power series where infinitely many of the coefficients are 0. Okay? All right, now, the main thing that we're going to be concerned with for power series is the following issue. So this sum, this infinite series, what it is going to depend on what x is, right? First of all, if it converges, then the value that it converges to will depend on x, of course. But also, depending on what x is, maybe it doesn't converge at all. Maybe it does for some x and for some x it doesn't. So those are the sorts of questions that we're going to answer. Essentially what we're trying to do is figure out the domain of this function. Okay? So that's pretty much what we're going to focus on in this lecture. Not just that function, but all power series. Okay, so we've got a theorem about the domain of these power series that motivates a few definitions. So let f of x, this is the sum from n equals 0 to infinity of Cn x minus a to the n, let this be a power series. Exactly one of the following statements is true. One and only one. Okay, first statement. It's possible that f converges, well, I guess I should call it f of x converges only when x equals a. That's a pretty boring case. It's boring because if x equals a, then every single one of these x minus a's is just 0. And then this whole thing is just 0. Okay? Well, except for the 0th term. So for this class, I know that in Calculus 1, probably a lot of you dealt with L'Hopital's rule concerned with indeterminate forms of type 0 raised to the 0, right? Okay, this is an indeterminate form. I'm not claiming that this has like a good reason for being what I'm about to say. For this class though, just for convenience sake, we're gonna say 0 to the 0 is defined as 1. Okay? That's not, we don't have a good reason for saying that. The only reason we want to say that is because we want to say that if x equals a, then this whole thing just becomes C0. Whereas, you know, if x equals a and we don't make this declaration, then you end up with 0 raised to the 0 as the 0 term, and then you're like, wait, what is 0 raised to the 0? Okay, so 0 raised to the 0, for this class, we'll just say it's 1. And in general, when you're dealing with power series, most mathematicians agree that 0 raised to the 0 should be understood as 1. Just because it makes things easier to work with. Anyway, so it's possible that f converges only when x equals a, in which case all of these terms are 0 except for the n equals 0 term. Okay, that's not a very interesting case. More interesting would be if f converges for all real x, and also interesting would be if there exists a positive real number let's call this capital R, such that f of x converges if the absolute value of x minus a is less than r, and f of x diverges if the absolute value of x minus a is greater than r. Okay? So these three cases are the only possibilities you could have. If you have a power series, then either it converges at only one point, at every point, or at some interval of points. Okay? And I just want to point out a few things about this. First of all, the terminology here is if it only converges at one point, we say the radius of convergence is 0. If it converges for all real values, then we say the radius of convergence is infinity. And if it converges whenever x minus a is less than r, but diverges whenever x minus a absolute value is greater than r, then we say the radius of convergence is r. Okay? All right, now, the first and second cases are fairly, well, hopefully they make sense, right? It either converges at one point or it converges at all points. In those two cases, yeah, whatever. But this third case, I think, is a little more obtuse, a little more difficult to see what's going on here. So let me try to explain. First of all, there's something that I want to just reframe your thinking about. So on a number line, let's say A is located right here, okay? Inequalities like this come up a lot in the field of math that I do. And when I see an inequality that looks like this, I don't pronounce this in my head as the absolute value of x minus a. I pronounce this in my head as the distance between x and a. Okay? And that's how you should think of it too. Think of this as the distance between x and a. All right? So what this is saying is that you have convergence when the distance between x and a is less than r. In other words, if you take a minus r, and you take a plus r, well, those are the 2 points where the distance from a is equal to r, right? What we're saying in this third case is that you have convergence in this open interval. Okay? So in this open interval from a minus r up to a plus r. So, in other words, you have 3 possible cases. Case 1 is that it converges at only one point, case 2 is that it converges at all points, and then case 3 is that it converges in some interval of points. Anyway, enough of this abstract discussion, let's get to some examples, because, of course, that's going to be more important. How to work with this. Also, one more just little piece of terminology. the set of points where a power series converges is just called the interval of convergence. So, yeah. So that will come up. So let's see how this works. So, the directions of all the examples I'm going to do in this lecture are exactly the same. We're going to find the radius of convergence and the interval of convergence of the power series sum from n equals 0 to infinity of -1 to the n divided by n plus 2 times x to the n. Okay. The way you do this, always, is you use either the root test or the ratio test, and then you set that less than 1, and then we'll go from there. I just want to point out, it's almost always the ratio test. There will be exactly one example today in which I don't use the ratio test out of the maybe like 10 examples that I have. So yeah, it's almost always the ratio test. So we'll start with that. We want the limit as n approaches infinity of the absolute value of an plus 1 divided by an. Well, this is the limit as n approaches infinity of, let's see here, absolute value of -1 to the n plus 1 times x to the n plus 1 divided by n plus 1 plus 2, well, I guess that would make n plus 3. All of this divided by -1 to the n, x to the n, divided by n plus 2, and it's the absolute value of all of this, right? Okay, so we're dividing two fractions, so we just have to copy the numerator, flip the division into a multiplication, and flip the denominator. So we have -1 to the n plus 1 times x to the n plus 1 divided by n plus 3, multiply by n plus 2 divided by -1 to the n, x to the n, absolute value. All right. Well, let's see here. If this is what you're dealing with, well, n copies of -1 cancel, right? And also n copies of x cancel. So what we're left with here is the limit as n approaches infinity, the absolute value of, well, let's see, I guess we're left with -1 times x times n plus 2 divided by n plus 3. Okay, so now when you take the absolute value of -1, of course that's just 1, so we can just forget about the negative. And then we're also taking the absolute value of x, right? And as for n plus 2 over n plus 3, those are both always positive, so we don't even have to worry about their absolute values. So this is the same thing as the limit as n approaches infinity of the absolute value of x times n plus 2 divided by n plus 3. Now, x is, well, you wouldn't say it's a constant for the power series, but it is a constant with respect to n. It doesn't depend on n, is what I'm saying. So that means you can actually pull it out of the limit. So this is the absolute value of x times the limit as n approaches infinity of n plus 2 divided by n plus 3. Limit as n approaches infinity of n plus 2 over n plus 3 is just 1. So this just turns out to be the absolute value of x. Okay. So the ratio test says we have absolute convergence as long as this is less than 1. So let's set this to be less than 1. Okay? And at the same time, if this is greater than 1, then we have divergence, right? Again, ratio test. So what we get here is that the radius of convergence is 1. Okay? And in general, whenever you get an inequality that looks like in order to have convergence, you need x minus a to be less than r, this r is always going to end up being your radius of convergence. So in this case, a is 0 and r is 1. Okay? So our radius of convergence that would be r equals 1, and that's at least one part of our answer. The other part is asking for the interval of convergence. Now let's think about this for a second. So, first of all, as I mentioned before, this is the distance between x and 0. Okay? So we need to think of this sort of geometrically. If we were to put 0 on a number line, what we're saying is that x has to be not a distance of less than 1 from that point, right? So to the left by 1, that gets you to -1, and to the right by 1, it gets you +1. So what we're saying is that x has to be contained somewhere in here, and if it is, then the ratio test guarantees us absolute convergence. Okay. And if x is outside of, if it's less than -1 or if it's greater than 1, then the ratio test guarantees us divergence in that case. But the ratio test cannot tell us anything about when x is actually equal to -1 or when x is actually equal to 1, the endpoints of the interval of convergence. Okay? So, in that case, we'll just have to test those points differently. So here's how it works. We're going to take x equals -1. Let's see, when x equals -1, this power series looks like the sum from n equals 0 to infinity of -1 to the n divided by n plus 2 times -1 to the n. Okay, -1 to the n, it might be 1 or it might be -1, but no matter what, if you multiply it by itself, you'll get 1. Okay, so these will just cancel. So this will be the sum from n equals 0 to infinity of 1 over n plus 2. Now is this convergent or divergent? Well, if you do the limit comparison test on this and the harmonic series, you'll find that the limit is positive infinite. So by the limit comparison test, this has the same behavior as the harmonic series. We know the harmonic series diverges, so this diverges too. Okay, so this is divergent by limit comparison with the harmonic series. Okay. All right, next up, I'm just going to erase this part. We already have the important information that the radius of convergence is 1, so I'm just going to get rid of this. And also, it's actually graphed up here, so whatever. Yes. So now, we've tested x equals -1. We found that we have divergence at x equals -1. We also need to test when x equals 1. When x equals 1, this looks like the sum from n equals 0 to infinity of -1 to the n divided by n plus 2 times 1 to the n. Now, of course, 1 to the n is 1. So then this becomes just the sum from n equals 0 to infinity of -1 to the n divided by n plus 2. And then our question is that convergent or divergent? That one is convergent according to the alternating series test. Okay, so this one is convergent by the alternating series test. And so what we're getting here is that this one we cannot be at -1 and get convergence, but we can be at +1 and get convergence. Okay? So what we're getting here is that the interval of convergence is specifically the interval where x is greater than -1 and less than or equal to 1. In other words, it's the interval from -1 to 1, open on the left and closed on the right. Okay? And so this is our interval of convergence, or in other words, the domain of f, the power series. Okay? And as you can see, the ratio test, it can give you a lot of information. It can tell you a lot of information about the interval of convergence, but it cannot tell you about the endpoints. As this example illustrates, it's possible that one of the endpoints will converge or diverge. It's possible that the other endpoint will also converge or diverge. In this case, they did different things. They could do the same thing too. Okay, and of course we'll see examples like that today as well. All right, so let's look at another example. Okay, next up we've got the sum from n equals 0 to infinity of x minus 2 to the n over 2 to the n. Okay, so this one is another power series. This one is a power series centered at 2. And again, we're going to do the ratio test. So we're going to say the limit as n approaches infinity of the absolute value of an plus 1 divided by an. This is the limit as n approaches infinity of the absolute value of, let's see here, x minus 2 raised to the n plus 1 divided by 2 raised to the n plus 1. Take all of this and divide it by x minus 2 raised to the n divided by 2 raised to the n. And then, you do the normal algebra thing where you're dividing a fraction. So you just copy the numerator, change the division to a multiplication, and flip the denominator. So we have x minus 2 to the n plus 1 divided by 2 to the n plus 1 multiplied by 2 to the n divided by x minus 2 to the n. Well, of course, you have n copies of x minus 2 canceling. You also have n copies of 2 canceling. And, of course, you don't have to worry about the absolute value of 2, because that's just 2. But you do have to think about the absolute value of x minus 2, okay? Because that might not be positive. So this is going to be the limit as n approaches infinity. Let's see here. What we get is 1 over 2 times the absolute value of x minus 2. And so this is just a constant with respect to n. So if you take the limit as n approaches infinity, nothing happens. Okay, so this is now just 1/2 absolute value of x minus 2. And so the ratio test guarantees us absolute convergence if this is less than 1. It guarantees us divergence if this is greater than 1. All right. So if we set this to be less than 1, well, that's the same thing as saying that x minus 2 is less than 2. Just multiplying both sides by 2 there. Okay. And so this means that our radius of convergence is 2. All right, now, the center here is 2, and the radius of convergence is 2. So if we were to put this on some kind of number line, we have 2 here, and that's our center of convergence. We don't want to be a distance of more than 2 away from that point. So that means that we could go down to 0 or up to 4, but definitely not further than that. In fact, not even as far as those, because it has to be less than. Okay, so we're guaranteed absolute convergence as long as x is as greater than 0 and less than 4. And that's just ratio test. Okay, now there's still more to do because you might have convergence or divergence at the endpoints. That's not clear. And if they're asking for the interval of convergence as well as the radius, then, well, this is not enough. So we need to check those individually. We check when x equals 0. So when x equals 0, this looks like the sum from n equals 0 to infinity of 0 minus 2 to the nth power divided by 2 to the nth power. Okay, 0 minus 2 to the nth power, well, it's negative 2 to the nth power, which we can actually also write as negative 1 to the nth times 2 to the nth, and then the 2 to the nths cancel. So then this becomes the sum from n equals 0 to infinity of negative 1 to the nth power. That's divergent. Okay, that's definitely divergent because it's the limit of the terms is not 0. It doesn't even exist, so it's definitely not 0. So by the test for divergence, it's divergent. Okay, so this is divergent by the test for divergence. All right. Well, we also have to check when x equals 4. When x equals 4, we're dealing with the sum from n equals 0 to infinity of 4 minus 2 to the n divided by 2 to the n. 4 minus 2 is, of course, 2, and then the 2 to the n's cancel. So this is just the sum from n equals 0 to infinity of 1 And again, test for divergence indicates that that is, of course, divergent because I'm pretty sure 1 is not 0. So, divergent by the test for divergence. Okay. And so what we get here is that the interval of convergence, which I'm just going to abbreviate as IOC from now on, I guess. The interval of convergence is that you get convergence if and only if x is greater than -1, or no, not -1, greater than 0 and less than 4. In other words, the interval of convergence is the open interval from 0 to 4. Okay? So neither of these points grant convergence, only the points between them. So this is an example where the two endpoints have the same behavior. And of course, as I said, that can happen too. All right, let's do another example. So this one, is the sum from n equals 1 to infinity. Okay, let's see here. Sum from n equals 1 to infinity of -1 to the n, x to the n. So -1 to the n, x to the n, divided by the cube root of n. And this is from 1 to infinity. Okay. So, it's the ratio test. So again, we're just taking the limit as n approaches infinity of, let's see here, top is going to be -1 to the n plus 1, x to the n plus 1, divided by the square root of n plus 1. Take all of this and divide it by -1 to the n, x to the n, divided by the square root of n. Okay? So this is just the limit as n approaches infinity of the absolute value of -1 to the n plus 1, x to the n plus 1, divided by the square root of n plus 1, times the square root of n, divided by -1 to the n, x to the n. Okay, so n copies of -1 cancel. Not that it matters because we're taking the absolute value anyway. But n copies of x also cancel, right? So then this is just going to become the limit as n approaches infinity of the absolute value of x times the square root of n divided by the square root of n plus 1. And again, x is constant with respect to n, so that means that we can pretty much ignore it and just take the limit of this part, which is 1. So this is the absolute value of x. Again, ratio test guarantees us absolute convergence as long as this thing is less than 1. Okay, so that means that our center is 0, and our radius of convergence is 1. Okay. All right, so again, geometrically, that looks like you have 0 in the center, and then -1 is a distance of 1 away, and 1 is also a distance of 1 away. And so we need to check those endpoints. So when x is -1, this looks like the sum from n equals 1 to infinity of -1 to the n times -1 to the n divided by the cube root of n. And again, you're multiplying negative 1 to the n by negative 1 to the n. And no matter what, that's going to cancel. So this just becomes the sum from n equals 1 to infinity of 1 over the cube root of n, which can be written as n to the 1/3 power. 1/3 power. 1/3 power. There we go. Now, 1/3 is not greater than 1, and that means that that p-series is divergent. So this is a divergent p-series. Okay, so we don't get convergence at -1. What about at x equals 1? Well, when x equals 1, this looks like the sum from n equals 1 to infinity of -1 to the n times 1 to the n divided by the cube root of n, which of course is just the sum from n equals 1 to infinity of -1 to the n divided by the cube root of n. That one is convergent by the alternating series test. So this is convergent by the alternating series test. And then with that, you get that there's not convergence at -1, but there is at 1. And so the interval of convergence, that would be where x is greater than -1, but less than or equal to 1. Or in other words, the interval from -1 to 1, open on the left and closed on the right. Okay, let's do another example. Let's see. This one is -1 to the n, x to the n over n squared. Okay. So -1 to the n, x to the n over, just remove this cube root of n and replace it with n squared. Ratio test. So this is going to be limit as n approaches infinity of the absolute value of -1 to the n plus 1, x to the n plus 1 divided by n plus 1 squared. All of this is divided by -1 to the n, x to the n divided by n squared. And so this is just the limit as n approaches infinity of the absolute value of -1 to the n plus 1, x to the n plus 1 divided by n plus 1 squared, multiplied by n squared divided by -1 to the n times x to the n. And things cancel once again. And since we're taking the absolute value, those negative signs don't even matter. So this is just the limit as n approaches infinity of the absolute value of x times n squared over n plus 1 squared. And that limit is, again, 1. So this is just absolute value of x, and we need that to be less than 1. Okay, so center of convergence is 0, and radius of convergence is 1. So radius, you know what, I'm just going to abbreviate that too. I'm just going to abbreviate that as ROC. That's 1. So exactly the same diagram as the last problem. We're centered at 0, and we can only go out a distance of less than 1. So the question is, can you go out a distance of exactly 1? Well, let's see. If x equals -1, then this turns into the sum from n equals 1 to infinity of -1 to the n times -1 to the n divided by n squared. -1 to the n times -1 to the n is 1. So this is the sum from n equals 1 to infinity of 1 over n squared. And that is a convergent p-series. Because, of course, 2 is greater than 1. Now, if x equals 1, then this becomes the sum from n equals 1 to infinity of -1 to the n times 1 to the n divided by n squared, which of course is the same thing as the sum from n equals 1 to infinity of -1 to the n over n squared. And this is for sure convergent. There are actually two ways of seeing that. One way is by saying, well, this is the absolute value of this. No, sorry. This is the series of absolute values corresponding to this. So since this one is convergent, this one has to be absolutely convergent. Or alternating series test. Either way, we see that this is convergent. So I'm just going to say this is convergent by the alternating series test. Although this brings up an important point. It's absolutely convergent at x equals 1. But the ratio test did not tell us that. Okay? So what this means is that when you're at the endpoints of the interval of convergence, you might get divergence, you might get absolute convergence, or you might get conditional convergence. The ratio test is going to tell you nothing about that. Anyway, the interval of convergence is going to be, well, all the x values that are greater than or equal to -1 and less than or equal to 1, or in other words, the closed interval from -1 to 1. Okay. Next up, we have n to the n times x to the n from n equals 1 to infinity. So, if you guessed ratio test, this is the one time today that you were wrong. So, yes, this one is actually better done by the root test. So we're going to take the limit as n approaches infinity of the nth root of the absolute value of the nth term. In our case, that's going to be the limit as n approaches infinity of the nth root of n to the n x to the n. Okay, that happens to be the limit as n approaches infinity of nx. Well, okay, I guess we should have absolute values here. So n times the absolute value of x, really. Not that it makes much difference, though, because as n approaches infinity, this will always approach infinity unless x is just 0. Okay, so this is less than 1 if and only if x is 0, which means that we get convergence at exactly 1 point. Okay, so the radius of convergence is 0. The interval of convergence, it's just the set of 0. And when we're talking about a set of only finitely many elements, we use these braces to indicate that, and we just list the elements. So that's that one. Okay, so that was the weird one. All right, now let's see about 2 to the n squared x to the n. All right. Ratio test. So I just want to point out, the thing that indicated for that last problem that you should use the root test rather than the ratio test is the fact that you had something dependent on n raised to something dependent on n. Okay? Like the coefficients were n to the n, right? Basically, when the root test is a good thing to consider whenever you have something that depends on n, like just n, raised to something else that also depends on n, like just n. Okay? Other than that, it's pretty much always the ratio test for a power series if we're trying to find the interval and radius of convergence. Okay, so ratio test. We take the limit as n approaches infinity of the absolute value of 2 to the n plus 1 multiplied by n plus 1 squared times x to the n plus 1. Divide this by 2 to the n squared, x to the n. Okay, well, that's the limit as n approaches infinity of 2 times n plus 1 squared divided by n squared times the absolute value of x. If you want this, well, first of all, as n approaches infinity, n plus 1 squared over n squared just approaches 1. So this just approaches 2 times the absolute value of x. And we want this to be less than 1 in order to guarantee absolute convergence. Okay. So now I just want to point out, this is the same thing as saying absolute value of x is less than 1/2. Okay? And so what that tells us is that our radius of convergence is actually 1/2. Okay, so we have a center at 0, and we can't go further than 1/2. So now all that's left is just to test the endpoints. Well, if x is negative 1/2, then what we're dealing with here is the sum from n equals 1 to infinity of 2 to the n squared, negative 1/2 raised to the n. This is the same thing as the sum from n equals 1 to infinity of 2 to the n times n squared times negative 1 to the n times 1 over 2 to the n. The 2 to the n's cancel, so then you're just left with the sum from n equals 1 to infinity of negative 1 to the n squared. Well, that's an alternating series, but it definitely doesn't pass the alternating series test. In fact, as n approaches infinity, n squared also approaches infinity. So the limit of the terms doesn't even exist. So by the test for divergence, this is divergent. So this is divergent by the test for divergence. Now if x equals positive 1/2, then we're dealing with the sum from n equals 1 to infinity of 2 to the n squared, 1/2 raised to the n. And again, the 2 to the n and the 1/2 raised to the n cancel each other, so all we're left with is the sum from n equals 1 to infinity of n squared. And that's definitely not any better, right? Okay. This is also divergent by the test for divergence. And so what we get is divergence at both endpoints. So our interval of convergence is only where x is greater than negative 1/2 and less than 1/2. Or in other words, not the closed interval, but rather the open interval from negative 1/2 up to 1/2. All right. Next up, we'll look at negative 1 to the n minus 1 over n 5 to the n x to the n. So, negative 1 to the n minus 1 over n 5 to the n x to the n. From n equals 1 to infinity. So it's the ratio test. So we do the ratio test. The limit as n approaches infinity of the absolute value of, I'm just gonna get right into the multiplication. So this is negative 1 to the n plus 1 minus 1, which is of course just negative 1 to the n, times x to the n plus 1 divided by n plus 1 times 5 to the n plus 1 multiplied by n 5 to the n divided by negative 1 to the n minus 1 x to the n, absolute value. Okay, so some things cancel. This turns into the limit as n approaches infinity of the absolute value of, well, you know what, nothing's gonna matter with the absolute value except for x, right? So let's just say the absolute value of x, the negative ones cancel and whatever, and then you get one factor of 5 on bottom, so we have 1/5, and then you have n divided by n plus 1. So now as n approaches infinity, this approaches 1, and so this becomes 1/5 absolute value of x. And that has to be less than 1 in order to guarantee absolute convergence. So therefore, we have absolute value of x has to be less than 5 in order for the ratio test to guarantee absolute convergence. So the radius of convergence is 5. And the center is 0. So once again on our number line, we just have to start at 0 and go out by a distance of 5 on either side. Let's see here. If x is negative 5, then this becomes the sum from n equals 1 to infinity of negative 1 to the n minus 1 divided by n 5 to the n times negative 5 to the n. Okay, so now this turns into sum from n equals 1 to infinity of, let's see here, so we have negative 1 to the n minus 1 times negative 1 to the n. That's actually just going to give us negative 1, okay, because it's the same as negative 1 to the 2n minus 1. So we have a negative sign. The 5 to the n's cancel, And then what we're left with here is just 1 over n. Well, that's a constant times the harmonic series, which is divergent. So this is divergent. Since it's a constant times the harmonic series. Okay, and also we need to check if x equals 5. So if x equals 5, this becomes the sum from n equals 1 to infinity of, let's see here, negative 1 to the n minus 1 divided by n 5 to the n times 5 to the n. The 5 to the n's cancel. So now this becomes the sum from n equals 1 to infinity of negative 1 to the n minus 1 divided by n. That's the alternating harmonic series, which is conditionally convergent according to the alternating series test. So this is convergent by the alternating series test. So what we get is that the interval of convergence is all the x values that are greater than negative 5 and less than or equal to 5, or in other words, the interval from negative 5 to 5, open on the left and closed on the right. Okay, I suppose here's another weird one. So this one is going to be the sum from n equals 1 to infinity of x to the 2n divided by n factorial. Now at first, this might not look like a power series at all. You might be saying, well, this isn't really a power series because this isn't raised to the n, it's raised to the 2n. It is a power series, though. It is because this is the same thing as the power series sum from n equals 1 to infinity of Cn x to the n, where Cn is just 0 if n is odd, and 1 over n factorial, actually, well, I guess it'd actually be, well, I should write this differently. So we'll call it k equals 1 to infinity, ck x to the k, where ck is 0 if k is odd, and if k is even, then this becomes 1 over k over 2 factorial. Okay. The details are not super important for right now. They'll become more important later on when we talk about Taylor series. But for right now, just know that this is a certain power series. Okay? It's just the coefficients have a piecewise function. Anyway, we're going to do the ratio test here. So this is the limit as n approaches infinity of, let's see here, absolute value of x to the 2 times n plus 1 divided by n plus 1 factorial times n factorial divided by x to the 2n. And then, you know, things cancel. So this becomes the limit as n approaches infinity of x squared. Well, I guess it's actually the absolute value of x squared, but that doesn't really make a difference, divided by n plus 1. Okay. Well, as n approaches infinity, it doesn't even matter what x is. This is always going to be 0, right? And of course, that's always less than 1. So what we see here is that no matter what x is, we are guaranteed absolute convergence by the ratio test. So the radius of convergence is infinity, because it converges on all the real numbers. And the interval of convergence is, well, all the real numbers, which is just the open interval from negative infinity to positive infinity. Okay. Now let's see here. I've got a couple more examples, which I will leave you to read yourself. Example 1195 and 1196. They're not really harder than the ones that I've done. The reason why I'm leaving them out is actually because they're just pretty much the same thing. But we'll do one more. This one is the sum from n equals 1 to infinity of 2x minus 1 to the n divided by 5 to the n times the square root of n. Okay, and once again, you might be saying, wait, is this even an actual power series? And it is. It is a power series because you can factor a 2 out of these two terms here. You get 2 times x minus 1/2, right? And then that you can screw around with so that it turns into the form of a power series. In any case, we're going to take the limit as n approaches infinity of the absolute value of 2x minus 1 to the n plus 1 divided by 5 to the n plus 1 square root of n plus 1. This is multiplied by 5 to the n square root of n divided by 2x minus 1 to the n. So now, once again, the only thing that the absolute value really matters for is 2x minus 1. So this is the limit as n approaches infinity of the absolute value of 2x minus 1 multiplied by 1 over 5 multiplied by the square root of n divided by the square root of n plus 1. Now, as n approaches infinity, of course, the square root of n divided by the square root of n plus 1 approaches 1. So this now becomes 1/5 absolute value of 2x minus 1. And the ratio test guarantees us convergence only if this is less than 1. Okay, now this is the same thing as saying that the absolute value of 2x minus 1 is less than 5. Now you might be thinking that that means the radius of convergence is 5, but it's not, okay? Because the radius of convergence, remember, we always need to have an inequality that looks something like this. The fact that we have a 2 there in front of the x is screwing this up, okay? So what we need to do here is factor out the 2. We can say that this is 2 times the absolute value of x minus 1/2. Then we can divide both sides by 2 and get x minus 1/2 is less than 5/2. And so our radius of convergence is actually 5 halves, or in other words, 2.5. All right, so on a number line, we've got our center of convergence at 1/2. Now to the left, we can go out by 5 halves, right? Okay, so let's see. 1/2 minus 5 halves, that makes -4 halves, which is -2. So we can go all the way out to -2. And we can go up to 1/2 plus 5 halves, which is just 6 halves, or in other words, 3. And now we need to check the endpoints. So, if x equals -2, this turns into the sum from n equals 1 to infinity of, let's see here, 2 times -2 is -4. Subtract 1 and you get -5. So this is -5 to the n divided by 5 to the n times the square root of n. This is the same thing as the sum from n equals 1 to infinity of -1 to the n, 5 to the n, divided by 5 to the n, square root of n. The 5 to the n's cancel. So now this is just the sum from n equals 1 to infinity of -1 to the n divided by the square root of n. Okay. That one is convergent by the alternating series test. So this one is convergent by the alternating series test. Now how about when x equals 3? Well, when x equals 3, we have 2 times 3 minus 1. That makes 5. So this is the sum from n equals 1 to infinity of 5 to the n divided by 5 to the n root n. The 5 to the n's cancel, and what you're left with is the sum from n equals 1 to infinity of 1 over the square root of n, which is the same as 1 over n to the 1/2 power. That's a divergent p-series. So this is a divergent p-series. So what we get here is that our interval of convergence is exactly where x is greater than or equal to -2, but less than 3. In other words, the interval from -2 to 3 closed on the left and open on the right. Okay? Anyway, that'll be all for today. Homework is up. Go ahead and get some practice.